So now a couple examples. So this is giving me the sum of a geometric series. So let's just say that I wanted to take that series we were working with before and just add up the first 5 terms. So 1, 2, 3, 4, 5. And so we're finding S sub 5. So according to the formula, it'll be A sub 1 minus A sub 1 times R. R is 1/2 in this case. So 1/2 to the 5th all over 1 minus 1/2. And so we could use our calculator, but this one's not too bad. 2 to the 5th is 32. So we have 1 minus 1/32 over 1 minus 1/2 is 1/2. And so we end up with 31/32 over 1/2, which is 31/32 times 2, which is 31 over 16. So getting close to 2, right? 32 over 16 would be 2. So, and you could double check this by, since 5 is not too many, you could just add them up and confirm that that is the right answer. So next question was, well, what happens if you keep doing this forever, right? What happens if you keep doing this forever? And so that's sort of like adding up till n is infinity. So if I flip it over, the rest of it is still the same. And so now we're just going to write s, and so no n. And so this is going to be the sum of the full thing. So it's going to be 1 minus 1 times r to the n all over 1 minus 1/2. And so the question is to this, what happens when n is really big? All right, and so n just keeps getting bigger and bigger and bigger and bigger. And so you keep taking half of a half of a half of a half of a half. And what's going to happen is that's going to approach 0. And so when n approaches infinity in calculus, we say that the limit is 0. And so this is going to approach 0. So that part's just gone when n is really big. And so I'm left with 1 over a half. So that sum actually is 2. So that infinite sum is 2. So when we keep adding terms, it just keeps getting closer and closer and closer to 2. And if we add up infinitely many of them, we actually get to 2. 2 is the answer. And so in general, the sum of an infinite geometric series, we can follow that same pattern. So the sum of an infinite geometric series is going to be a sub 1 minus, we would normally have that minus a sub 1 times r to the n, but that's the part that disappears. So I just get a sub 1 over 1 minus r. The catch is, of course, this part really needs to disappear, and that part's only going to disappear if it keeps getting smaller when n gets bigger. And it only gets smaller if r is less than 1, right? If r is bigger than 1, it's just going to keep getting bigger when n gets big. And we also have to make sure r doesn't go below -1 because of the same sort of problem. So this infinite geometric series only has a sum if r is between 1 and -1. And if it does have a sum, then we get a sub 1 over 1 minus r. So you can work on a few practice problems now. Just a couple things that you can think about sort of related to this that we can talk about tomorrow. What is 0.9999 repeating, right? So 0.999 repeating. In particular, is that the same thing as 1? Another one that's sort of fun to think about is sort of similar to the one we had just done, but this time we're going to square numbers on the bottom. So what happens when we have 1 over 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared and so on, which if you want to write it with sigma notation, k is going from 1 to infinity. So we're going to add those all up. So the sum of the reciprocal of the squares. So that'll be some good things to think about, and we'll talk more about it tomorrow, but otherwise get some good practice in, and we'll see you tomorrow.